Rear wings and splitter plates are very important when it comes to high performance cars. They not only produce downforce, which is vital for stability at high speeds, but they also control where the downforce is created, which helps with the handling of the car. For example, producing more downforce over the front wheels helps reduce understeer because the front wheels then have more grip and can hold the turning line better. Then on the other hand, rear wings in particular are even used for braking. In other words, rear wings that are traditionally used for downforce and hence reducing their drag was ideal, are now being used to produce massive drag at certain points during a car's operation to actually benefit the car. And among other ways to optimize splitter plates and rear wings, the way you mount them on the car can have large effects on their performance. And that is what we're looking at today. How does attaching the rear wing and the splitter plate, so the rear wing here and the splitter plate down here, onto the car, how does that affect the car's performance? And to find the answers to this question, we are looking at this paper called Numerical Study of the Sports Car Aerodynamic Enhancements. It is open access, so you can find that link below. So straight off the bat, the author and this paper was done by just one author actually, just lone soldiering it. And the author says that not only are there aerodynamic differences, but also mechanical differences to how you install these aero devices. So for example, in figure 3, at the top, we see the rear wing mounted to the car in two very different ways. So down here to figure 3. On the left, the authors call this the bottom mounted position because the wing is mounted from the bottom. And then on the right is the top mounted position because you can see these bars coming along from the top and mounting to the top of the wing, as you can see in these figures as well. So the top mounted wing from a mechanical point of view has more flexibility in how it is positioned. It can be moved around more. That immediately means that you can at least have a better chance of finding a good position for the top mounted wing than the bottom mounted wing simply because there is more options for the top mounted wing. In addition, the authors looked at different splitter plates, and in figure 8, if we scroll all the way down here, we see the different configurations that they looked into. So in the top row of figure 8, down here, okay, so here we go. In the top row, we have just a little lip coming off the front, so this little splitter here. Then in the next 3 rows, we have a splitter that can extend out. So it's completely retracted here. It can extend out like this. And then if you look at the last 2 rows very closely, let's zoom in actually so we can see it better. Almost, here we go. Okay, so we see that for this top row, there is a splitter plate that can extend outwards, but then there's this little gap between the actual splitter plate and the underbody of the car. For this configuration, there is no underbody gap. So there's a vertical plate coming down and that blocks the flow. Now, the reason why this author wanted to see how a retractable splitter plate affected the car's aerodynamics is because he says that this could very easily change the balance of the car, which is a good thing. Maybe you don't want so much downforce over the front, or maybe you want more, whatever. So if you have too much at the front, you can then move the splitter plate back, and if you need more at the front, then you can move it forward, or at least that's the general idea. We'll see later in this research if that actually works. But just quickly, let's go through how these two aero devices work so we know better the fundamentals before jumping into their changes in performance. So first of all, a rear wing is pretty obvious in that it is just a wing at the back and the air goes over it, as you can see in these figures here. And just one thing to keep in mind is for those from other fields, for example, aerospace engineering, when you have a wing, you have on a car, it's producing downforce. So you have high pressure on the top and low pressure underneath. That's often quite easy to forget and you get them mixed up, and there's different terminology for it. So for example, in aerospace, you would have the pressure side would be the underside. Here it's actually the top side, and the suction side, which would have been the upper side, is actually the lower side. So just keep that in mind. So the splitter plate are significantly more complex in how they affect the flow than a rear wing, generally speaking. First of all, they limit how much air goes under the car because as the air comes along and hits the front, when there is no splitter, some of the air can and will come underneath the car. So in this figure here, the flow comes along, it hits here and then it will come underneath a little bit. When there is a splitter plate, and the bigger that splitter plate is, the more it stops that air from bleeding underneath the car. And with less air going under the car, you can then get a better Venturi effect happening, which is where the air speeds up and the pressure drops. That then increases the downforce. So here you now have a huge surface, literally the underbody of the entire car, exposed to this low pressure. That helps produce a lot of downforce, and that is one way that splitter plates work. The other main way is that when the air comes along and hits the front of the car, it decelerates, so often by a lot as well. And that results in the dynamic pressure in the flow, so the movement of the flow, it gets converted into static pressure, and that is pressure that you can feel. And just by looking at the geometry, this high pressure is directly over the top of the splitter plate. So you have high pressure here directly over the top. So now you have this high pressure pushing down the splitter plate that creates good downforce and very far ahead of the front wheels. So you can produce a lot of grip on the front wheels just by using a splitter plate. And in a nutshell, that is how a rear wing works, and that is how a splitter plate works. So by modifying these Aero devices, you can hopefully control how much downforce you get and where, which makes the car faster around the corners as well as more stable. Now, to investigate these different wing and splitter plate configurations, this researcher used CFD, and the model was the Aerodynamic Husaria. I don't know how to pronounce it properly, but anyway, you can see it in figure 1. It's a pretty popular car actually for a lot of projects. I'm not sure why. Like a lot of times when you look at a paper, this car has been used. I guess it's just that it looks like a typical supercar. It has some nice aero features on it, so it looks pretty standard for a supercar. And for the rear wing, they tested 2 modes, one which is called performance and one which is called braking. For the performance model, the rear wing was pitched at 10 degrees, while for the braking mode, it was pitched to 55 degrees. Now, this is interesting because for the performance mode, 10 degrees is perfectly reasonable. That is well within a regular wing's operation conditions, and is actually quite close to the maximum lift to drag ratio you'd get for typical wings. I'm not sure what profile this wing is, but I guess it would be pretty similar to traditional wings, so about 10 degrees seems pretty decent. But for braking, I don't quite understand why 55 degrees was selected. I mean, if you want to maximize braking force from the rear wing, at least pitch it to 90 degrees. That would then maximize the frontal area and hence the drag. But maybe they don't go to such extreme angles because of the mechanism can't control it or handle it. I don't know. But anyway, I would have thought that aerodynamic-wise, a 90-degree pitch angle would have been better. Anyway, in figure 1, we see the domain, and they use an unstructured mesh. And you can see that immediately because of how the cells change in size. They go from very large, and they start to get smaller and smaller as you get to the refinement regions. And the domain was sized so that the cross-sectional area of the car was only 1% of the domain's cross-sectional area, which is great because that means that there is negligible effect of the car on the domain and vice versa in terms of aerodynamics. And I quite like this researcher's method description because he puts quite a lot of details in. That's good for a paper. You want to put in details so people will know what you're doing. So for example, he says that for the boundary layer mesh, he used 6 prism layers with a growth rate of 1.2. And you can kind of see these prism layers here if we zoom in a lot. It looks a bit difficult to see, but that's the prism layers there, that really thick black line, they're all scrunched together. And the growth rate was 1.2, as we said, which is pretty standard and good. And the Y plus values can be seen in figure 1D. Let's zoom in here. And this is a little concerning actually because, and interesting because you can see that almost nowhere is the Y plus value close to 1. It ranges from around 30 up to about 300. He says that overall, the average Y plus value for this car was 84, which is quite high. As for the wing and its mount, the average was around 38. Now, just because the Y plus was so high doesn't mean that the CFD is automatically bad. It really depends on the terminus model used because this researcher used RANds. And unfortunately, now we get to the kind of bad bit. So he used the K-Omega SST terminus model, which is great, except the Y plus is probably a little bit high. So for a regular K-Omega terminus model, then this will be really bad. But for the K-Omega SST terminus model, it is a bit better, but it's still a little bit high. I mean, fortunately, the K-Omega SST can take Y plus values up to 300 and still give decent results, which is what he had here. But whenever you go to high Y plus values, especially like 300, you rely more and more on wall functions to inform you what is going on near the wall. And these wall functions just aren't as good as if you were to use the K-Omega SST equations directly for the boundary layer. So by using such high Y plus values, you run the risk of having a bad boundary layer. And for most flows, the boundary layer is everything. It makes or breaks the simulation. So we will have to see how that goes later on. And we actually get some important information here concerning it right now, actually. He said that he used the steady state RANs, which isn't great either, especially when it comes to bluff bodies like cars. So circling back to the Y+, does that mean that the Y+ being very high matters? I would be inclined to say here that it doesn't so much because it is steady state RANs anyway, and the errors from this are already quite large, so the additional cells you would need to use to make the Y+ value below 5 or even lower probably wouldn't be worth it here. So either way, this researcher I think is very good at weighing his resources and determining what is worth using or what is just, if it's just a happy coincidence, I'm not too sure. But I think he kind of weighed it properly and thought like, okay, I can increase the number of cells that I have, but I'm using steady state RANs anyway, and that doesn't really make much of a difference then. So anyway, what that means for us is that we probably can't trust exactly the numbers for the downforce and the drag, but we should be able to trust the trends because the differences in geometry are very large. I mean, you have this wing either at performance or braking is very different. The splitter plate is coming out a lot more sometimes. So while this setup isn't very accurate, I think it should be accurate enough to get a decent idea. Let's move on. So this researcher used just half the car's geometry in the simulations, which isn't great because cars typically have periodic flows and that affects the forces. The free stream flow was 60 meters per second, which is 260 k's per hour. Now, one thing that this researcher is strong in more than other research on cars is that he set the turbulence intensity to be 5%, which is far more representative of on-road conditions. Now, the wheels were modeled as stationary, so no rotation. I think this isn't a great choice by the researcher because, okay, I can understand that he is trying to save as much time as possible for the simulations, but even just putting a rotating wheel boundary condition on the wheels and closing the rims a lot more would have been okay and added almost nothing to the simulation time. In fact, closing the rims might actually have saved some cells because if you look at these rims here, they are very spoked. So you can see a lot of spokes here, and spokes usually take up a lot of cells to refine. So anyway, would this stationary wheel approach affect the results much? For the rear wing, probably not much because the effects of the rotating wheels are mostly localized to the underbody. For the splitter plate, I think it would have been pretty okay too here because it is very upstream, and especially when it's extended, it's very far away from the front wheels. So I think the stationary wheels here might change things a few percent, but okay overall. You could have just put in a rotating wheel boundary condition here and it would have been much easier and it wouldn't have added anything to your simulations. Now in figure 2, we see the grid independent study. He tested 1 million cells, 2.3 million cells, and 4.6 million cells. And that's great. He really increased the number of cells between meshes a lot, and that's really good for CFD simulations. A lot of research doesn't do that, so he really nailed that here. And from figure 2, we see that he pretty much reached mesh independence by about 2.3 million cells. It doesn't change too much after that, maybe a few percent difference between the medium and fine meshes for the drag coefficient, and the same for the lift coefficient. So for some reason though, he decided to use 4.6 million cells, which I don't know why, because the 2.3 million cells would have been fine still, at least from this grid independent study. And at least what we can tell from this mesh is that it's independent. So what I would have done actually is checked the entire car and then taken the 2.3 million cells and then did the entire car. So applied it to the entire car instead of half a car and had 4.6 million cells. So that way you have the same number of cells that you have here, but it's for the entire car, and then checked how that performed. Anyway, we can conclude that this mesh has reached convergence based on his level of desired accuracy. Let's move on to the validation study now. So the validation data comes from the experiments in the Aero wind tunnel, which is the most well-known automotive wind tunnel in the UK. It's kind of past its heyday now, but still pretty good. It's one of the leading ones in Europe at least still. Now we come to a bunch of information that differs to the CFD setup. First of all, this car was a full car in the wind tunnel and not half a car. The CFD was half a car. Secondly, the flow in the wind tunnel was 35 meters per second, so almost half of 60 meters per second here for the CFD. Now that isn't great because there will probably be some differences, but because the flow will be very much turbulent, the differences in the Reynolds number won't affect the results that much here at least. It would be much more different if it was like 10 k's per hour and 100 k's per hour. So anyway, in fact, the more I read this setup, the more it reminds me of the early CFD setups done in the 90s and the early 2000s. All of these CFD simplifications were pretty much done back then because they didn't have the computational resources to do more realistic simulations. And the CFD back then was usually within about 15% of the results from the wind tunnel. So I think that this error here that we're looking at is about 15% too. Now, one major difference in the car between the CFD and the experiments is that the car tested in the wind tunnel was the GT version of the Aero. The biggest difference between that and the regular car is that the GT version had an additional air intake on the roof, which the CFD one didn't have. As for the drag and lift coefficients, the authors say that the drag coefficient was about 3.8% different, and the lift coefficient was about 6.5% different to the experiments compared to the CFD. Now, I don't think that this means that the CFD is good to within 5% because there were too many differences still. I think it is more around the 10 to 15% mark that we have from like the 90 CFD kind of thing. That's my opinion at least. Anyway, let's move on to the results and keep in mind that they are either about 5% off or in my opinion about 10 to 15% off. So in figure 3, we see the rear wing and how it is connected, and then the streamlines around the wing when it is retracted compared to in the performance mode, which is this second row here, and then in the braking mode, which is the final row here. So in the left column, we have when the rear wing is attached to the car through that bottom mechanism. Then on the right column, we have when the rear wing is attached to the car on with the top mechanism here. And the colors represent the pressure coefficient, and we see the color bar here ranges from -2 for the blue, so that's a lot of good downforce effectively if it's on the top surface, to 1, which is the red, which can be causing a lot of drag, as we'll see. So when it comes to the upstream faces, like in the bottom row here, we see a lot of red on this rear wing. And that means that that is a very high pressure coefficient, and that is what you want when you want to brake. So when you flip this rear wing up, you want to create a lot of high pressure there, which then effectively results in a lot of drag, assuming that the backside of the wing is low pressure, which I imagine it would be here. But for performance, you don't really want this high pressure because that leads to a lot of drag, and that's not what you want. So this bottom row, luckily, it does produce a lot of, what we can see at least, potentially a lot of braking force, which is what we want. But for the second row, we see there is a little bit of a red at the front at the leading edge, which is not great, but that's really how it goes for rear wings and wings in general. Now, for the top row, we see when the wing is retracted, and there really isn't any difference that I can really tell between the flow physics when the car is mounted, the rear wing is mounted from underneath compared to on top. So the mounting struts seem to be fairly streamlined, I guess. The pressures look about the same. When the wing is in the performance mode, again, so the second row here, I can't tell too much of a difference. The only thing that stands out to me is that when the wing is mounted from the top, it can stick out into the flow more. You can see it's much higher up. That typically results in better downforce because it is in cleaner flow, but also the low pressure on the underside is moved away from the car. So that means that the car isn't producing as much lift on the actual top surface, and hence more downforce is produced. And that is in fact kind of what we see here. So for the left figure, looking under the car, let's under the wing, sorry, let's zoom in a bit here. We see that there is a green color, and that's significantly lower pressure than the yellowy kind of light green that we see for the other wing. So indeed, it seems to be happening here where I can't see the underside actually of the wing, but I would be tempted to say that the wing mounted on the top is producing more downforce simply because of this major difference here. We don't have the actual car itself cancelling out some of the downforce that the car will be producing. Now for the bottom row, when the wing is braking, I think the right figure has higher pressure near the wingtips. You can see there's a more red region here near the wingtip compared to a yellower region here, and that should convert to more drag. But equally interesting is that if you look again on the car surface, there is a very red region for both of the wings. So if we zoom in here, there's a really red region here and a really red region here. That tells us, this is actually very clever, that tells us that when the wing is deployed like this, we still get some downforce because it is kind of in a similar manner to a splitter plate where the air comes along, hits the front of this wing, decelerates a lot, converts that dynamic pressure to high static pressure, and that high pressure is over the car's surface. That then pushes the car down. Now, I think the left wing is better in this particular case for this mechanism than the right, because you see that for the right wing, it is mounted a bit higher, which results in the flow being able to go underneath. And that not only means that it has to accelerate to go through, but the wing isn't producing this like real air dam effect as much. It is still producing a little bit, but not as much in my opinion, what I can tell from here. Now looking at table 1, we now have some lift and drag coefficients, some actual figures here. So overall, as the wing is tilted more and more up from completely retracted to performance mode to braking, we can see that the drag and coefficients do change quite a lot. And fortunately, a lot of the time it is greater than the 5 to 10 to 15% error that is occurring in the CFD. For both wings, the drag coefficient continues to rise, which makes a lot of sense because, as we saw before, even in the performance mode, your wing is still using the flow and producing some kind of useful stuff out of it. That almost always comes with a drag penalty. And surprisingly, in the braking mode, there is like a double the downforce in the performance compared to the performance mode. So we see here, for example, it's minus 0.4 compared to minus 0.15, minus 0.37 compared to minus 0.27. So maybe the braking mode should be named the performance mode because you get so much more downforce as well. Anyway, Between the two wings, there are some differences again, but I'm not too sure how much is due to the error. I think that only one that really stands out is that in the performance mode, so this middle column here, this middle row, sorry, the top-mounted wing has almost double the downforce compared to the bottom-mounted wing, minus 0.27 compared to minus 0.15. That is probably because the clean flow can get to it, and it is away from the car, as we mentioned earlier, so the car doesn't counteract the downforce with its own lift, so that makes a lot of sense. Now in the braking mode, the numbers suggest that the bottom-mounted wing is better than the top-mounted wing, but I think this is borderline in the uncertainty of the CFD. I mean, from figure 3 in the bottom row, it makes sense, I guess, because of the aerodynamic effect is strong for the bottom-mounted wing. So I don't know, maybe this is an error, maybe it isn't, I'm not too sure. Anyway, in figure 4, we get some more information about the wing's performances. So this is figure 4 here. And it's a little confusing, but let's try to go through it because there's some really good insights as to what's going on. So in the left column, we have the velocity, and that goes from 0 to up to 90 meters per second in the red. Then in the right column, we have the pressure coefficient. Again, it goes from -2 to 1. Then the top two rows are for the retracted wing. So we have these two rows. That's for the bottom mounted compared to the top mounted. And there's almost no difference here. The wings are pretty much identical. Like, it's really bang on each other. There's maybe a little bit of lower pressure over the top surface of the wing here for the bottom mounted compared to the top mounted, but it's pretty much the same. And just as a side note, the car does well already kicking the flow up at the back. So the diffuser is working pretty good here. That indicates there is already some pretty good downforce being produced. Now for rows 3 and 4, so these ones here, let's zoom in a little bit. Here we go, that's better. So this is for the performance mode. So the wing is popped up to about 10 degrees angle of attack, and for the bottom and top mounted wings respectively. Now we can see that the top mounted wing it's performing perhaps a little bit differently. It's because it's moved away from the car. There is less low pressure on the car's surface as we suspected. You can see it's like a little bit better. That is why in table 1 we saw better downforce. We also saw that for the bottom mounted wing, the flow zips underneath it better, which results in lower pressure on the underside. As you can see here, it's a little bit greener compared to yellower here. And that's because the wing is just too close to the car's surface, and that doesn't help produce downforce, unfortunately. Finally, in the bottom two figures, this is for the braking mode. So the wing is popped up at 55 degrees. And you can really see that for the bottom mounted wing, so this row here, the velocity is much lower over the car. And that comes with a lot higher pressure as well. So you can see more red around upstream on the car, as we suspected was happening. But just as a side note, I think that the top mounted wing support would also be stronger from a mechanical point of view. I'm not sure what the forces are on this wing, but in the extreme case, like a rocket sled or something, the top mounted wing would be more mechanically sturdier, and it could result in a bigger wing that you can put on it. So that's just another aspect to consider. So the researcher recognized the problem of the top-mounted splitter, rear wing here, in that it let air through this small gap more, and during the car's braking. So he tried to improve the wing as shown in figure 5 down here, and he had some pretty interesting results. So we have 4 different setups. The original one, which is in figure 5A here. Then he had it where he moved the wing down more, so the exact same wing, just down more. Then he has in figure 5C where he molded the leading edge of the wing effectively to effectively follow the contours of the car. Then in figure 5D, it's the exact same wing as he had originally, but now he put a little lip, a little spoiler on the back of the car to hopefully block off some of that flow. So in table 2, we see the effects of these efforts, and they're really interesting. Actually, had some pretty good success in some of them. So we see that with lowering the wing, so figure 5B, that's just the standard lower it doesn't change at all, had almost no effect, maybe a little bit lower drag, but again, that's potentially in the error of the CFD. Contouring the wing to the rear had a really large effect, so we had about a 50% increase in the downforce, which I think is definitely outside of the CFD error, and a bit of a higher drag as well, which in the braking mode is pretty good too. Then when he tried the one more thing where he had that same old top-mounted wing and in the same position, but just had the spoiler at the rear, so it helped block off the flow underneath the wing. This approach worked the best with like 2/3 more downforce and the highest downforce out of all these different configurations, and then 15% more drag. So that's an all-round improvement for this braking mode. So I guess it kind of makes sense because spoilers are there to produce downforce anyway, and also blocks off the flow, so best of both worlds. So this is really good thinking from this researcher. He had a pretty good final result here. In figure 6, let's move on to that one here. So this is the side view of these new rear wing designs. And again, the left column is for the velocities and the right column is for the pressure coefficients. And for the contoured wing, so this third row just here, we see just how much more the wake shoots up compared to the original situation. It's really almost like an F1 kind of wake. And in fact, in the final design, it's even more extreme where the wake gets pushed up even greater. And that's a strong indication that more and more downforce is being produced. When you shoot up a wake, that's indicating that you're directing the flow that way. And that's either downforce or lift, depending on which orientation your object is. So that's very clear from these plots here. So that is the rear wing. But we also look at the splitter plate now, and how much does changing not only extending it out, but also mounting it differently to the car affect the car's performance? Well, in table 3, we see the drag. Let's go down to table 3 here. We see the drag and the lift coefficients of the splitter with these different setups. We can see that among the different setups, the drag coefficient isn't affected too much. I say that because, okay, well, in table 3, we do see a change up to about 8% perhaps. That is around the uncertainty of the CFD, so we can't say conclusively that one splitter setup was definitely lower than the other. Having said that, it seems like positioning the splitter lower and then having a vertical plate to stop the flow going through, so this bottom one here, increases the drag, and that makes sense because you're capturing even more of the flow, halting it in its track, converting the dynamic pressure to static pressure, almost stagnating it, and that means you have very high pressure over the splitter plate, and that's going to push the plate down, and also a lot of drag on the actual car itself, the horizontal surfaces and vertical surfaces together. So likewise, this particular configuration also dramatically increases the downforce because of that. So it went from minus 0.27 to 0.574 overall. That's a huge increase. And comparing it to the next best one, it's like 25% greater still, and that's greater than the uncertainty of the CFD. So that's pretty trustworthy, and that makes sense too. And we'll see exactly later in a second when we look at the pressure plots what's going on. Now, one interesting thing is that literally any splitter configuration tested gave much better downforce than the base geometry, which only featured a small lip like jutting out, as we can see in figure 7 here. There's really no splitter plate, it's just this tiny little thing. And all splitter configurations pretty much double the downforce or more of the entire car. Let's now get into why the splitter configurations have these effects that we saw in table 3. So figure 7 is a nice one, but it doesn't really show us too much. It's hard to compare each setup here. So let's go to figure 8 where we can see a lot more. So once again, we have the velocity fields in the left column and the pressure fields in the right column. Looking at the bottom row first, which is the best performing splitter, that was this deployed splitter with vertical plate. The drag is arguably about the same, but the downforce is way better, and we can see why. In the right figure, the pressure coefficient is far greater over the splitter plate compared to its main rival, this third row here, which means that you have a large horizontal surface with very high pressure over the top, and that pushes the plate down and the entire car down 2 more, and that is literally as far away from the front wheels as you can get. So that's like an extreme front wheel downforce. And the reason why there is so much high pressure over this splitter is this vertical plate at the back, this tiny little thing back here. Let's zoom in actually. This tiny little thing just back here, which the other plate doesn't have. So what happens is the flow comes through. It's much harder for the flow to go through, and that in turn does increase the pressure because the flow has to slow down and some of the dynamic pressure is converted into static pressure. But when you have the vertical plate, that happens even more. So this one does have a contraction and there is some sort of back pressure, and that does help a little bit. But the plate here is almost stagnating the flow in comparison, and that we can see that comes with a greater pressure coefficient over the splitter plate. As such, there is much greater pressure here and much greater downforce. From these plots, it is logical that there is more drag as well, so perhaps the findings in table 3 were still valid across the board. Now comparing the third row, which is the splitter completely extended and a little down, so there is a little gap here, and then the second row here, which is where the splitter isn't extended and there is no gap at the back. Immediately, we should be able to say that the extended splitter will produce much more downforce because again, you have a much greater horizontal surface area with very high pressure over the top. But Table 3 doesn't agree with that. I mean, for the second row, there's high pressure just in that tiny gap. So if we zoom in here, you see there's high pressure just in that tiny gap between the upper surface and of the car and the splitter plate. But then the underside of the car is also seeing high pressure, and that kind of cancels out. So you have high pressure on the splitter plate, high pressure underneath. You'd think that would cancel out from the splitter plate, so you wouldn't get too much of a difference. So to me, the results for the retracted splitter in table 3 is a little unexpected, and it doesn't make much sense, and I think this perhaps is in the CFD error. Alternatively, perhaps you could argue that the retracted splitter has lower pressure on the underside compared to the extended splitter, and that is what is causing the downforce now, so you actually get some suction on the underside. I'm not sure if that is the case or not. It's a bit hard to tell without further information and the uncertainty of the CFD. Anyway, comparing now rows 1 and 2, so row 1 here, which is for the regular car compared to the retracted splitter, table 3 tells us that the retracted splitter should give us a higher downforce by about almost 50% really. And that definitely agrees with the pressure coefficient plots that we have here. So because with the original front, the pressure coefficient underneath is much higher, you can see here it's like yellowy green as opposed to bluey. I think that that is because the flow travels around a lip more in this original car. So it comes along here, it can get around much easier. Whereas for this splitter, it comes around, hits the front, comes around, gets trapped in the underside of the car between the splitter and the car, and it can't zoom around a little bit. So that means we have less flow going underneath the car, which means it's not accelerating as much, which means we have lower pressure. Alternatively, you could argue that maybe there's just some stall going on here, and that's creating that low pressure. Overall, these results are pretty interesting, and some expected ones and some curveballs. So let's move on to now table 5, where we see the lift coefficients of the front and rear, so the distributions over the car of the various Aero devices and their modes. So table 5 is just here. Let's zoom in. Here we go. So for all elements retracted, so this number 1 case, the car has a positive lift coefficient overall, which is bad for handling, but at lower speeds, it is fine, and that also drops the drag, so it's not too bad in that case. For the rest of the configurations, the car is producing anywhere from a little bit of downforce to a lot of downforce. I mean, look at this last one here. This is minus 0.72 over the rear. And one great thing is that they dramatically change the balance of the car. So, for example, when you just have the splitter plate, there is more downforce over the front, but with the braking mode down here, there is crazy downforce over the rear and a little bit of lift really over the front. So there is such a range of options you can choose from, which is great for picking which ones are best for handling. As a general comparison, this author gives the lift coefficients of the front and rear of a few supercars in table 6. So we have Porsche 911, we have Bugatti Chiron, and Bugatti Veyron. One thing to note is that for most of them, they have more downforce over the rear than the front. Also, the Porsche 911, they have lift for some of the configurations, which isn't great, but again, that's mainly for the low speed cases. For the performance cases, now we get downforce over the front and rear and a bit more over the rear. So that brings us to the end of this podcast. It was really interesting to see how these different configurations affected the downforce and drag of the supercar. I really liked it. And one thing that I thought was awesome was that flipping the rear wing up for braking is beneficial in not just increasing the drag, but dramatically increasing the downforce over the rear. That might need to be coupled with the splitter at the front fully extended to get more downforce over the front and stop understeering. But it's cool that this happened really. So one final thing that I want to say is the study here had a lot of CFD, and if you want to learn how to do CFD or get better at it, or learn OpenFOAM, which is a free CFD software but hard to learn, take our course below, and we have ones that go all the way from completely noob all the way up to expert. And if you're doing aerodynamic experiments, did you know that you probably have a 2 to 4% error in your data and you don't even know about it? That is because the atmospheric conditions are constantly changing from day to day and even hour to hour. So in the atmosphere help link below, we go through the math of why and how to fix it. So if you like this podcast, hit the like and subscribe buttons, and we'll see you on. Peace amigos.